Our next speaker is Rosa Valiante, and she will tell us about from the first stars to the first galaxy, the first black hole. Sorry.
Thank you. First of all, I would like to thank the organizers for giving me the opportunity to have a talk in such a beautiful venue. And as Priya was pointing out in her exhaustive review, what we do know is that supermassive black holes are observed up to redshift about 7 during the optically bright quasar phase of active galaxies. These black holes are as massive as their local and lower redshift counterparts, but they have mass formed in much shorter timescale. What we do not know is what is the nature of these supermassive black holes, and in particular, how, when, and where the seed progenitors form, and how they rapidly grow up to the supermassive stage. As you have already heard, possible pathways to the first black holes have been proposed so far, from the population tree star remnants giving birth to up to a few hundred solar mass black holes, but it seems that the accretion timescale required to these stellar mass seeds is relatively long to form and grow a supermassive black hole at redshift 7, so that they seem to require an uninterrupted gas accretion at the Eddington rate or supercritical growth in the host galaxy. We have investigated this possibility in the work that Edvige Pezzulli will present later. The faster and alternative scenarios are, as you have already seen before, the direct collapse scenario or the intermediate mass black hole forming in the dense nuclear stellar clusters. In my work, I focus on the relative role of light and heavy seeds in the formation of the first supermassive black holes at redshift 7. In particular, we have selected the quasar J1148 as a target to our study, as it is representative of its population at redshift about 6. This is one of the most distant and best studied quasars, both from the observational and theoretical point of view. It has a black hole mass of about 3 times 10 to the 9 solar masses, and it is expected to be hosted by a massive dark matter halo of 10 times to the 13 solar masses. In order to investigate the relative role of light and heavy seeds in the formation of these supermassive black holes, we have used our semi-analytical data-constrained model for the formation and evolution of quasars and their host galaxies. You can find all the details of this model in this series of papers here, and in particular, I have been working in the evolution of dust and black holes. In each progenitor galaxy of the merger history of the host dark matter halo, we consistently follow the star formation in both mini and atomic cooling halos, the black hole formation combining the formation of POP3 remnants and direct collapse black hole of 10 to the 5 solar masses, and of course their subsequent growth, in this case in the Eddington limited accretion scenario. All these processes are regulated by the complex interplay between the mechanical, chemical, and radiative feedback that we actually take into account by modeling the effect of galaxy scale winds, the dust and metal enrichment of the ISM and of the external medium in which the halos are embedded, and of course the UV radiation, the effect of the UV radiation from both the stars and the AGN in each galaxies. In our model, we form population tree stars in the smallest halos in the merger trees, where when the metallicity is lower than this critical threshold here. Otherwise, population 2 star, second generation less massive stars form in the most metal-rich environments. We adopt a Larsen IMF with these characteristic masses and these mass ranges for the two populations of stars, but in the lowest mass halos, where population tree stars form, we stochastically sample this intrinsic IMF according to the stellar mass formed. In particular, we randomly select the stars in this mass range until we reach the total stellar mass formed in each halo. These are 3 examples of this stochastic procedure in which we form a larger number of stars as the total stellar mass formed progressively increases. This, for example, is a case for a low-mass mini-halo in which we form 6 stars and no black holes. As you can see, this is the region for the black hole formation. But you can also expect, for example, that you form a single 100 solar mass star. The other 2 cases are representative or more common halos, and the intrinsic IMF is fully sampled if the total stellar mass form is larger than 10 to the 6 solar masses. With these ingredients, we can also investigate, beside the effect of the chemical enrichment inside and outside each galactic halo, what is the effect of the UV radiation on star formation. Here, I show the redshift evolution of the Lyman-Werner flux density in the upper panel and of the H2 regions filling factor in the lower panel. All the lines are the result of the average of 10 different merger histories of the same quasar, with the shaded regions representing the 1 sigma dispersion. Here we compare the contribution to the Lyman-Werner emission from AGN and stellar sources. With this model, we have included in our computation, of course, the critical threshold for the direct collapse scenario to occur when the halos are exposed to a strong Lyman-Werner flux. Actually, this value is quite uncertain, and you will hear more about this problem in the following talks. In our model, we have selected as a reference value the intermediate case, but we have also investigated the possibility that this threshold is lower or larger. In this figure, I show what is the effect of the radiative feedback on star-forming halos. Here we have the minimum mass of star-forming halos as a function of redshift, the black line. And if you look at high redshift, you see that this mass increases due to the effect of H2 photodissociating feedback and reaches the minimum mass expected for atomic cooling halos, the blue line, already at redshift about 20. At lower redshift, this minimum mass still increases due to the effect of the photoionizing photons. And as you can see, it reaches at a given redshift, at a given point, about let's say 13, the typical mass of star formation occurring in ionized regions. The take-home message is that the star formation in our model in mini-halos is suppressed already at redshift 20 and below, independently of the merger tree resolution mass that is indicated by the red curve here. Indeed, if you look at this curve, the assumed resolution mass for the merger trees affect the minimum mass for star-forming halos only at redshift about 11. With this ingredient, we can investigate what are the properties of each single galaxy potentially hosting a light or a heavy seed. In this case, I show the number fraction as a function of redshift for light seeds. The histogram is the average, again, over 10 different realizations, with error bars accounting for the 1 sigma dispersion. The distribution of the number fraction of light seeds reflect the birth environmental condition of these population tree remnant black holes. In particular, we start forming first stars and light seeds at redshift 24. But the number of these light seeds is quite small, down to redshift 20. This is due to the fact that they are forming in this redshift range in mini-halos where the star formation is low and is strongly affected by the H2 photodissociating feedback. Then, by redshift 20, the number increases, or the number of light seeds increases, as they are mainly formed in the atomic cooling halos, which are less vulnerable to the radiation feedback. Then we stop forming first stars and light seeds at redshift about 15 when all the galaxies have been enriched above the critical metallicity threshold, that is 10 to the minus 4 solar. Here, instead, I show the distribution of the number fraction as a function of heavy seeds as a function of redshift. As you can see, the heavy seeds form in a very narrow redshift range. And they peak at about redshift 16, while the light seeds formation peak at an earlier redshift. This sudden appearance and decline in the number fraction of heavy seeds reflects the tight conditions required for the direct collapse scenario to occur. And in particular, the direct collapse black hole formation happen in a very small number of halos and over a relatively short period of time. More or less, about the 80% on average of these heavy seeds have been formed at redshift about 16.5. We can now investigate what is the relative role of these black hole formation channels in the growth of a supermassive black hole like that of J1148, which is indicated by the red data point here. The black line is the total black hole mass evolution, including mergers and gas accretion, while the red and the blue line indicates the contribution of light and heavy seeds without taking into account the gas accretion. Although they are more numerous than the heavy ones, the efficient gas accretion in the Eddington limited scenario is activated only if you form even one heavy seed. As you can see here, you need to form the heavy seeds to activate an efficient black hole growth. In our scenario that is Eddington limited, the conclusion is that heavy seeds are required to form a supermassive black hole at redshift 6. One of the advantages of using a semi-analytic approach is that we can actually investigate different independent merger tree realization of the same quasar, investigating what is the dependence of the number of heavy seeds and of light seeds on the particular merger history. Here I show 10 different realizations of the quasar J1148, and again we have the black hole mass as a function of redshift. As you can see, of course, the number of light and heavy seeds depend on the specific merger tree. For example, the larger is the redshift, here, for example, at which light seeds start to form, the larger is their final contribution. As you may have noticed, in 9 out of 10 of these realizations, we are well in agreement with the expectation of J1148, with the exception of this realization here. In this case, we do not form heavy seeds, and light seeds are not enough to explain a supermassive black hole at redshift 7, as long as the accretion is Eddington limited. We have investigated also, thanks to our semi-analytic approach, the parameter space. If you, for example, increases the Lyman-Werner background threshold for the direct collapse to occur, you end up in a scenario in which you do not form heavy seed at all. In this case, only light seeds, more numerous light seeds are formed, but you end in a 10 to the 6 solar masses. That is not enough, even for the higher gas accretion that we are assuming to form a supermassive black hole. This confirms the conclusion that in the case in which you form only light seeds, super Eddington accretion growth is required. We have also tested the case in which the transition between population 3 and population 2 stars is driven by dust cooling. This means that we assume that population 3 stars and light seeds form only when the dust-to-gas ratio is below this critical threshold. As for the larger Lyman-Werner threshold, we end up not forming heavy seeds, and thus we cannot produce a supermassive black hole at redshift 7. This is why the dust-to-gas ratio critical threshold in this scenario is exceeded well before the metallicity critical threshold here. These are my conclusions. We have seen that we are able to form from few up to 30 heavy seeds that are able to form before the metals and dust, in some cases, have enriched all the galaxies in the merger tree. The growth of the final supermassive black hole relies on the formation even of a single heavy seed in the Eddington limited accretion scenario. A larger value of the Lyman-Werner critical threshold for the direct collapse scenario, or a dust-driven POP3 to POP2 transition, is preventing the formation of the so-called heavy seeds. But most importantly, we now have a powerful tool which enables us to identify black hole seed progenitors of the first supermassive black holes according to the properties of their host galaxies. And we are able to study the conditions that allow these seeds together to form and grow at such high redshifts. So I'm done. Thank you.
Questions? No questions?
Oh, yeah.
Mike Norman.
Yeah, very nice work. I
Thank you.
think it would be very profitable if we compared your results with the Renaissance simulations, because we're basically doing the same problem in different ways.
You've seen that, sir.
My question is, am I to understand that you're using the Lyman-Werner background to suppress the H2 formation in halos and not, a nearby galaxy?
We actually compute, let's say, the average Lyman-Werner flux at which each galaxy in our merger tree is exposed to. We cannot follow the spatial distribution, but still, we are in a very biased region of the universe, and we can say that this kind of flux contributed to all the stellar populations, and AGN inside each galaxy is representative of the mean value in this, let's say, 50 megaparsec cube.
I see. So you're modeling a biased region.
Exactly.
Okay, thank you.
Thank you.
Yes.
There.
Here. Can you run the microphone?
Now there too.
Very nice talk.
Thank you.
My question is about the critical metallicity from the transition from population 3 to population 2. So a paper by Kazu, Rafael, Zoltan discussed the dust cooling efficiency in the atomic cooling halo. Is your critical condition is the same as the critical metallicity?
Yes.
Okay, like in terms of the solar metallicity, like a 10 to the 5 solar metallicity.
It goes to 10 to the minus 5 to 10 to the minus 3. We are just in the middle.
Okay, okay. Thanks.
And the dust-to-gas ratio is the same in that papers,
okay,
actually.
Question back there.
No, actually, it was a clarifying comment to Mike that actually in the work that I was talking about earlier, we all do the same thing. We average the Lyman-Werner flux by looking at a specific region. So what I showed you earlier was calibrated from the Phoebe simulation.
Yeah.
So we're not invoking just one particular stellar population, but we're taking into account the contribution from the various halos. But of course, it's dominated by the one that is closest, if you will. So.
We would have time for one more question.
maybe this is a little bit technical, but I was wondering if you include the effect or radiation transfer effects for the Lyman-Werner radiation, like the opacity.
No, of course not, because we don't have the spatial distribution for this. We cannot follow the variation with the radius, for example, from the source to the other galaxies. So we cannot take this into account.
But for instance, for the background, the sphere of influence, so there is basically like an horizon that is much smaller than
we take this into account, actually.
Okay.
We suppress the radiation coming from outside this horizon.
Okay.
Thanks.
Very quick question, Volker.
Where? No.
5 seconds questions, 15 seconds answer. Okay.
Rosa, of course, many of us, we like the idea of the direct collapsed black holes, including you and me. And of course, we believe that they existed in the universe. But let's say that a few years from now, the observers tell us with 100% certainty that those objects never existed. And how would we tune up our models to wipe them out?
We already have the alternative scenario. We have investigated the possibility in which you just start from light seeds, allow for short periods of supercritical growth, and then you make the supermassive black hole.
The question is, of course there are alternatives, but if we have to wipe out, because in the models, right, you have said you have conditions for the DCBH to form.
Yep.
And now, what would you have to do to not allow DCBH to form, to prevent them from forming?
It's not quite difficult. It's more difficult to allow the formation for the direct collapse, actually. If you increase just a little bit, for example, the metallicity threshold, you cannot form the heavy seeds already. Or if you use, for example, the dust-to-gas ratio as a limitation for the direct collapse formation, or even if you increase a little bit the threshold for the Lyman-Werner flux, you have a lot of solutions. The real problem is to find the solutions for forming the heavy seeds. That's quite difficult.
Okay, let's thank Rosa one more time.
Thank you.
Our next speaker is